by Greg Valiant.
Okay, yeah, so this is what I said I would talk about, but I'm actually not going to talk about this. It's, like a month ago, whenever I sent my abstract, I assumed things would be written up and on archive by now, and, the price to pay for optimism. Anyway, it's coming soon. Okay, so instead I'm going to talk about this other work, which is, I'm really excited about it. So I'll talk about sort of what's some previous work, which kind of sets the stage for hopefully a lot more work. So anyway, I hope you excuse the substitution of this talk for what I was originally hoping to tell you about. But anyway. Okay, so towards instance optimal testing and learning. Okay, so the basic setting, in general, when one thinks of testing or estimation of properties of distributions, you want to know, well, how many samples are necessary to maybe learn a distribution, to estimate a property value of the distribution, or maybe do some hypothesis testing to test whether, say, the distribution possesses some property of interest. Okay, so this is like a huge caricature, and I don't want to offend anyone, I'm sure I will, but so kind of the theoretical computer science view of these problems has been trying to get tight worst case bounds for various classes of distributions for various of these problems. But these are worst case over some sets of distributions. And worst case kind of in some non-asymptotic regime. Okay, so you have some fixed distribution parameterized by something or other, and what can you say? There are tons of exceptions, but certainly the old statistics view is the goal is slightly different, so optimal asymptotic rates of convergence. So there you're saying we fix some distribution, and we want to design algorithms that as the number of samples you draw kind of gets large, at least in the asymptotic sense, you should be doing something optimal. Okay, and both of these perspectives have offered us great results, good insights on how to actually get things to work well. But okay, so what I want to try to push, which is maybe impossible in some settings, certainly a bit naive, but so what do we really want? Well, we kind of want some sense of instance optimal performance. So we'd certainly like to understand the sample complexities of the tasks we care about on kind of an instance by instance basis, and I'll give one very concrete example of what that means. But as opposed to asymptotic rates of convergence, as opposed to worst case over various classes, we'd like to know kind of on every instance what's going on. And we'd also like to develop algorithms which leverage whatever structure is present in the instance, but we don't want them to need to assume prior knowledge of that structure. Okay, so that you give them your samples, they should be able to figure out what structure is there and leverage it, but not know ahead of time. Okay, so these are both, optimistic and a bit naive. Okay, but as am I. So, okay, so just to give one sort of very concrete illustration of kind of this sort of approach, which falls slightly shy of this lofty goal, okay? But I'll give a sort of extended description of this one setting. So, okay, hypothesis testing for distributions. Okay, extremely basic problem. We're given some epsilon greater than 0, and someone comes and tells you a distribution P. So they say, I have a big bag of jelly beans. I tell you, P1, there are 10% of the jelly beans are blue. 5% of the jelly beans are red. 30% of the jelly beans are green. Okay, someone comes and describes a distribution to you. And then you get to draw samples from this unknown distribution. And your job is just to decide, is the distribution equal to what I told you it should be? Or is it far? Is the distribution of jelly beans different from what I promised you it was? Far, say, in total variation distance. Okay. Basic hypothesis testing. Any? Okay, so what's known about this? So I mean, this is an instantiation of the kind of stuff that even Pearson was working on, a century ago. And in the TCS community, so this work of Batu et al. Basically showed that if you have a distribution that's over support size at most n, then you basically only need on the order of square root n samples to do this hypothesis testing. Okay? And the intuition here is kind of a birthday paradox, right? So the intuition is you don't really need to see the whole distribution. All you need to do is start to have some sense of kind of how many collisions are going on, and then you can already start to deduce is this distribution actually what it's meant to be or not. Okay, so one specific distribution that people care about is testing uniformity. So give you this unknown distribution, you want to say, is it the uniform distribution over n things, or is it far from that? Okay, so Goldwright and Ron were looking at this problem, and they also showed, okay, this root n over some poly epsilon dependence, and the right answer for testing the uniform distribution is this root n over epsilon squared. Okay, so Paninsky showed this, and this really is just the birthday paradox. Okay, among distributions supported on n things, the uniform distribution minimizes the number of collisions. So once you start to see some collisions, then you kind of can count how many collisions you've seen, and you basically know, is it uniform or not? Okay, that's what's going on here. And okay, so these are nice results. These are some specific distribution results. These are some worst case over some class of distribution result.
So you're saying Paninsky is tight?
Yes. Yeah. What we'd really like to know is, well, kind of what does this curve look like for different distributions? If I give you an easy distribution, if I describe some slightly easier distribution, you'd like to know how do you leverage what this distribution is to design a better test and to actually figure out, exactly what the sample complexity is for this specific task, okay, instead of some worst case or some specific result. Okay, so this is what we do. So we show that there exists some fixed function f. It's a function of the distribution you describe, n epsilon, and there are constants. And our tester can distinguish the case that the unknown distribution is equal to this thing that was described versus the case that they're far, using this f of p comma epsilon samples. And no tester can distinguish this using kind of up to constants more samples. Okay. And yes, we're losing constants both in front of the epsilon and in front of the f. This is necessary for not so subtle reasons, but okay. Okay, so what is this function f? So it's slightly ugly, but it's not that ugly, and it's surprisingly clean, given that it's optimal to constant factors. Both these terms are necessary, and so on. So what is this? Well, it's a max of 1 over epsilon. Okay, you certainly can't hope to do this using fewer than 1 over epsilon samples. So it's a max of this term and the second term, which is basically the 2/3 norm of the vector of probabilities after you've removed the largest probability and you removed all of the small probabilities up until you've taken away epsilon mass. Okay. Okay, so this is, and we'll parse this a little bit. Okay, so just one thing to note. This expression, this is always at most just the 2/3 norm of the vector p. So immediately, if p is a distribution supported on at most n elements, the 2/3 norm is at most root n. And so immediately this shows that actually this root n over epsilon squared, so Paninsky's tight result for the uniform distribution, this is worst case bound for all distributions supported on at most n elements. Okay? But for easy distributions, this will get you lower sample complexity.
Is this like the worst case scale divergence between Q and another P or something like that?
No. So I'll give you a bit of intuition where this comes from, but
I guess in hypothesis testing, scale divergence usually pops up.
yeah. Although there it's kind of so there it's usually you're saying, is it this thing or that thing? Here we're saying, is it this thing or is it far from this thing, right? And so now it's, is it this one, close to this one distribution, or is it, part of this huge set of distributions? So that's why that's the difficulty in this sense.
Question.
Do you require the tester knows that it knows?
It actually, so the question was, do you require that the tester knows that it knows? And the point is, given this number of samples, it will. So it doesn't.
But it doesn't. The tester can't compute this number, right? Because it depends on p.
No. So P. So I tell you, there's a mystery bag. Sorry, P isn't the mystery distribution. P is. Yeah. Yes. Right. Sorry.
Just the previous. Can you go to the previous slide? So the blue line should actually just touch the magenta line, or?
So the blue is, it's not, so basically, it's not tight. This polylog isn't there. So our results imply that actually the blue line can be improved to root n over epsilon squared.
Just touch the magenta.
Yes.
Yeah. If you require the tester to accept also when the two distributions are close within epsilon prime, do these methods generally?
So that gets much harder. So, right. So, root n over epsilon squared samples for any distribution supported on n things, you can test are they equal or far from equal. If you want to test is their distance less than 0.01 versus is their distance more than 0.99, there you actually need like n over log n samples if you're a distribution supported on at most n things. Okay, so the one-sided versus two-sided error is actually very different. It's almost this quadratic relationship. Okay, so I'll actually tell you the test that achieves this, and it's something very intuitive. It's actually very similar to Pearson's chi-squared test. Okay, so Pearson's chi-squared test is it's a very general tool, and for this specific problem, we're going to make two slight tweaks to it, and we'll actually achieve this kind of, in some sense, instance optimal testing. Okay, so again, someone describes the distribution P to you. You take some samples from distribution Q. Let xi be the number of times you've seen the ith element. So both these tests are basically saying, look at the difference between the number of times you see the ith element and the expected number of times you've seen it. Square this and subtract something like the expected number of times you're going to see this and divide by pi. Okay, so this term and the denominator, these are deterministic. Okay, I've written it this way just because basically we're going to replace this by its expectation. Sorry, by its, the random variable who has the same expectation, namely xi, kind of in the good case. Okay, and instead of normalizing by pi, we normalize by pi to the 2/3. So what's the intuition behind these things? So in the case where we're actually taking samples from P, replacing this by xi doesn't change the expectation of this quantity. Okay? But the claim is it really reduces the variance. So why is this? Well, most of your variance comes from very rare elements. Okay? So the intuition is, how many samples do you need? Well, you take samples, and then you should stop at the right time. And you should be able to stop when there's still lots of things that you've only seen once and twice, right? Otherwise, you've taken way too many samples. So most of the variance will come from things you've seen 0 times or 1 time, things that you might see but probably won't see. And the point is, if the expected number of times you're going to see the I thing is very small, if this k times pi is almost 0, then this is like xi squared minus xi, which is basically 0 if xi is either 0 or 1. So you pay nothing for things you've seen either 0 or 1 times. Whereas in this case, if there's something that's rather rare, you probably won't see it. If you do see it, then this really kills you, because now this is like, you know, a 1 squared over pi. This really hurts. Okay, so this first substitution is to decrease the variance. Okay, the second, that's normalizing by the 2/3 power, this is a bit more subtle. So it basically says, look, you know, you see some things appear more often than you'd expect, some appear less. To what extent should you be weighing? So if I see something that, you know, differs from my expectation, and I see it many times, I should care a lot about this. So if someone says, look, half the jelly beans are red, and the empirical number of jelly beans I see is very different from 50%, I should be troubled, right? If someone says, oh, this jelly bean occurs as probably 1 over 100, you know, I'm more willing to tolerate errors in the light elements. And that's what this 2/3 reflects, that I'm a bit more understanding of deviations from the expectation for elements that don't appear very often. Okay? And the intuition for why it's exactly 2/3, there's no good intuition. If you try to think about this problem from the point of view of upper bounds, you end up with kind of thinking that you should get one exponent. From the point of view of lower bounds, you get a different exponent. So yeah, so this comes out of the proof. Okay, so how do you analyze this sort of thing? Well, you know, conceptually it's very easy. So it's going to be an application of Chebyshev's inequality. Okay, so we have some quantity. We want to analyze its expectation, its variance, and so on, right? So when you try to do it, you end up with sort of inequalities that basically look like this. So these are, you know, these are pretty ugly. It's conceivable that you'll be able to try to prove it, but it's not gonna make for a nice paper. So the next part of the talk, I was just going to mention this analysis tool, which basically turns this into just an automated thing. You just press enter, it tells you how to prove this, done. And I wanted to mention it here because, you know, we've all sorted through this sort of thing. It's not fun, and you know, maybe now you don't need to.
What order are we supposed to read these in?
Well, okay, so this is the thing, right? So someone like you can probably just march through this, but yeah.
It's the sum of those two
Oh, sorry. There's a plus sign here. That's what you're asking?
vertical terms is less than the thing on the right.
Yes. That's what you need to prove to argue that the test will work with good probability. Okay, so I haven't mentioned lower bounds. So we have matching lower bounds, right? The soft malady thing, some Hellinger distance stuff. There are some tricks, but I thought I would mention this instead, since it's a bit more.
But do you have intuition as to why this 2/3 of all things is helping out?
No, I mean, you know, so this is work with my brother. We split up. He worked on lower bounds. I worked on upper bounds. After 2 weeks, we reconnected. He said, "No, it's the 1/2 norm." I said, "No, it's the 3/4 norm." And we were both wrong for sort of dual reasons. And yeah, so if someone has a good intuition for why it should be 2/3, I would like to hear it.
So if you change it, then one side doesn't work, right? If I make it 2/3 plus delta, then the theorem's not true.
Yeah, then either the tightness or the I can't figure the convexity of these things. I'm not good at doing on the spot, but yeah, either the lower bound just ceases to be tight or the upper bound won't work. Okay, so I'll quickly tell you about this.
Does it still give square root and upper bound? Instead of 2/3, if you have like 3/4 or a half, does it still give you the?
Oh, yeah, but it ceases to be tight for some distributions. Yeah, whereas we want to be tight for kind of everything. So you can think of this as also. So say someone tells you, listen, we're gonna, everyone likes the blue jelly beans, but they cost more since the blue dye is expensive. So, and blue ones are rare. So let's trick them. We'll tell them it's 10% blue, but we're actually going to add fewer blue jelly beans. And the question is, how much can you play with the probabilities without me noticing? So if something is meant to appear half the time, you can't play with that probability too much. If something's meant to appear only 10% of the time, you can play with that probability more. If something only appears 1% of the time, like relative to 1%, you can play with that probability a lot. And the question is, how much, how does this amount of play decay, or how does the relative amount of play increase as the probabilities get small? And it's exactly this 2/3 norm. So that's the kind of dual interpretation as how do you design a tricky thing that you're not going to notice? How much error can I stuff in without someone finding out? Okay. 4 minutes? Okay. 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 So clear your head for a sec and consider the following question. Pure math question. Say someone gives you three sequences, sequence of A's, B's, and C's, and they ask you, is it true that for all positive sequences x, j, and yj, this inequality holds? The product over I of the sum over j of the xj's to the A's, y's to the B's, the whole thing to the C's. When is this always greater than 1? So I claim that actually a lot of the inequalities we know and love fall into this class. Okay, so Cauchy-Schwarz has this form. Right? You pick A to be the vector 1, 0, 1/2, B is 0, 1 1/2, C is 1/2, 1/2, minus 1. This turns into this product, which is Cauchy-Schwarz. Holder's inequality also has this form. You just replace the halves by lambdas, this by 1 minus lambdas, and so on. What other inequalities have this form? So it turns out this kind of monotonicity of the LP norm has this form. Just the fact that x plus y squared is greater than x squared plus y squared. Okay. Right. So that also has this form. What other things have this form? Well, we can multiply any of these, and we have other true inequalities of this form. But is there anything else? And the answer is no. So this thing is true for all positive sequences if and only if you can express this as a finite product of Holder-type inequalities and LP monotonicity inequalities. Okay, and so we show that actually we give it this algorithmic characterization. So if it's true, we can efficiently tell you how to prove it, how to decompose it into Holder and LP monotonicity things. And if it's false, we can efficiently find you a witness, which is a bit surprising because I can describe one of these things with sequences AIs, BIs, CIs of bit length n, such that the shortest counterexample sequences have like doubly exponentially many terms. Okay. Okay. So maybe I'll quickly do this geometric interpretation of the theorem. I won't tell you how to prove it. I'll do this nice geometric interpretation. So
then, to be efficient, so it's a construction rather than actually you give me the sequence, because even storing that sequence would be very difficult.
Yeah, so it tells you sort of how you could write it out. It gives you a witness to the existence of it. Yeah. By the way, there's MATLAB code that on our websites that does this. You just enter in the A's, B's, and C's. It tells you if it's true, and if it is, it tells you how to prove it. And this is what we use to write up our paper. It's super easy. Okay, so first, though, I want to just give you this geometric interpretation, and this might be all I have time for. So say you want to prove this inequality. For all positive sequences x's and y's, this is true. This actually is one of the components of this thing that we needed to prove. So let's just plot these things on the plane. The exponent of x is the x-coordinate, exponent of y is the y-coordinate. The weight is the exponent outside. So the theorem can be interpreted as saying that this inequality is always true if and only if we can zero out all of these values via two types of moves. So the Holder type move, where we can take any two positive numbers and we can move them to their weighted average. And then LP monotonicity thing where we can slide any negative value towards the origin and increase its weight. Okay, so let's play this game. So what should our first move be? Well, we have these two positive numbers, some negative thing in between them, so, we can take 1 unit of each of their mass, and move it to their weighted average. We cancel out the negative thing. Okay. Now what should we do? We want to make everything disappear.
Get rid of the minus.
Yeah, so let's get rid of this. Namely, let's slide it on the line towards the origin and scale up its mass. Okay, so this is a Holder inequality, this is LP monotonicity thing corresponding to these moves. Okay, and now we have these 3 collinear things, and lo and behold, if we move the 2 outsides to the middle, all of them vanish. And lo and behold, if we multiply these 3 things, if we multiply these 3 equations, we get exactly this. So we've proved our inequality. And in some sense, our theorem shows that, there's an efficient algorithm for deciding how to win this game, if it's winnable. Okay, and even though there are an infinite number of moves, intuitively kind of only a finite number of them really makes sense, right? Okay, so I guess I'll skip the proof of this. And I'll just end with, so further directions. So this characterization of these inequalities applies to sequences of 2 things. What happens if you have more positive sequences? And the answer is the exact same characterization holds. It's quite a robust kind of phenomena, and it seems to be new in part because the proof is very algorithmic. So it's a little different from the usual math proofs of this sort of thing. And this is going back to this instance optimal property estimation and learning. So the setting I described, this hypothesis testing, is sort of easy because I'm telling you this distribution P, and then you get to tailor your algorithm for that instance. So it's not as instance optimal as one would hope. But in more general settings, it still might be possible. We have some results that hopefully will be ready to be discussed in the next week that are kind of really nice. And anyway, so in general, if you can do some instance optimal sort of algorithm, it's likely to have a nice theory, and it's also likely to work quite well in practice. And so that's kind of the so maybe I'll end there.
So we'll take a quick question while the next speaker sets up. And of course, I'm sure many of you have many more questions, which we'll save for the discussion session. So, yes, David.
Yes.
On that point about knowledge of P,
Yes.
what about the problem which is very similar, but suppose I give you 2 sequences, and I ask you whether they're from the same distribution or they're from 2 different distributions, different by more than epsilon. Then you don't have P at the tester.
Right. So then right. So you can define some analogous sort of instance optimal sort of setting where you'd want to say something like you'd like to do at least as well as if I had almost described this distribution to you. So say I tell you that I describe some distribution that's close to the true distribution ahead of time, and you'd hope to do as well as if you actually had known this. Right, Alon wants to say something.
I think this problem is talking about closeness testing. And
right, okay. You have some negative results, right?
no, positive. So we can show that you can do closeness testing. We have the boundaries you can get on them, and also for classification. What you call instance by instance, we call competitive. So for that problem, the more complicated still problem that you have 2 training sequences and you have a test sequence, you can also do that. i.i.d here and tilde here for the
Sure, but so there though, so you do lose something, right? So the competitiveness is.
So we get results that are independent of domain size, like regardless of what your support size is.
And we also show that everyone has to lose something. You cannot be optimal everywhere.
Yeah.
And whatever you can do, we also show some positive results. So you can achieve.
Yeah.